Okay, we have started the recording today, the 21st. Let's begin by taking a moment to remind ourselves some major achievements we achieved last time. What did we do? Let's look at the chalkboard last time. We're interested in the motion of rigid bodies. And one of the first things we're going to do is look at the angular momentum. So we worked out the angular momentum for a rigid body, and here we have discussed a rigid body which consists of a collection of particles somehow magically glued together with massless glue, so to speak. So we have fixed interparticle distances and angles. And if you have a collection of particles, then the mass distribution is described by, first of all, a collection of values for the masses. So these m sub alphas, these are the individual masses of the particles. And then the positions, r sub alpha, those are the position vectors for each of the individual particles. The velocity vectors, we know from the useful relation, can be gotten via this cross product. The rigid body is assumed to be in a state of rotation. The instantaneous axis of rotation is given by this lowercase omega vector. Okay, and what we did last time was we proved that the angular momentum is equal to a matrix times the angular velocity. So in general, the angular momentum could point in a different direction. Sometimes it does point exactly in the same direction as omega, but sometimes it's a different direction. Okay, so this equation here, which is written using vector notation for the vectors and this special double-headed arrow for the matrix, this is a very compact way to write it. The same equation now written out in detail in components is written like this. Okay, so the angular momentum vector here, we exhibit the x, y, and z components. We arrange it as a column vector, that's standard. And the same is true for the angular velocity vector. We arrange the three components into a column. We got this column vector here. And this wonderful new thing, the inertia tensor, also called the moment of inertia tensor, is a 3x3 matrix. It's a rank 2 tensor. Today we're going to talk some more about what it means to be a rank 2 tensor and other tensors as well. And this is standard matrix multiplication. If you have a 3x3 matrix, and this would be a 3x1 matrix, you use the same conventions that we used for the indices. First, you talk about the first index there, tells you how far down to go. The second index tells you how far to the right. And so in the same spirit, this is called a 3x1 matrix. The 3 is the number of rows. The 1 is the number of columns. That's a 3x1 and that's a 3x3. So that's an example. We know there are very general rules for matrix multiplication. For example, in Physics 89, we talk about this. You can multiply any two rectangular matrices. The one thing that is required here is that the number of columns in the first factor must equal the number of rows in the second factor. Then you have a well-defined matrix product. Okay, so last time what we did is we delved deeply into this triple product, right? We have a cross product and another cross product. The triple product we simplify using the back cab rule, and we arrived at these wonderful results for the components of the inertia tensor. In principle, there are 9 components here. We're going to show that we have a symmetry. We're going to show that Iyx is equal to Ixy. Okay. When we wrote the matrix, we were very careful with the distinction with the first and second indices, because we want to be careful looking ahead to other matrices that we'll talk about, which are not symmetric. And when we say symmetry, that's of course the symmetry about the main diagonal. Okay. But in fact, the inertia tensor has a nice symmetry. Okay, it is a symmetric matrix. It's the usual notion of symmetry about the main diagonal. And that means that the Iyx is equal to the Ixy. The Izx is equal to the Ixz, etc. Let's take a second to prove that. So in proving this, we'll review what it means to be a component of the inertia tensor. It means that you're a coefficient. If you are a component of this matrix, then you are a coefficient. Okay, so here's Ix, for example, Ixx. That means we're looking at the x component of the angular momentum. This is gotten by taking the first row in the matrix and forming a dot product with this nice column vector here. And here we've written out that dot product explicitly. In other words, these three capital I's with the appropriate indices are the coefficients. So let's look at over here. We did a calculation last time. This is what we did. We wrote out the vector triple product, and then we explicitly wrote out the details for the x component, the y component, and the z component of the angular momentum. Having done that, we can read off the capital I coefficients, right? We begin by looking for any occurrence of omega x here in the first result. That was the Lx result. Well, there's an omega x here and there's an omega x here, and that got us this first coefficient, okay? In the same spirit, we can look for the Ixy component. It's the multiplicative factor in front of omega y. There's only one occurrence of omega y in Lx. That was the first row of this result. Here's the omega y, and you see the prefactor is a minus x alpha y alpha together with the mass and the summation. Okay, let's now investigate the symmetry. This coefficient here, the Iyx coefficient, means you look at the y component of the angular momentum, and that was our second of these three major results. And now you look for any occurrence of omega x, because we're interested in the Iyx. Well, the omega x occurs right here, and again you see the multiplicative factor, in this case the minus y times x. Okay, so that shows the symmetry, and the off-diagonal elements, they all have this structure. So Ixy is, you see the minus sign, so we're summing over the masses, and then we have the x alpha and the y alpha as given by these indices here. And so in that sense, we immediately have proven the symmetry because this multiplication is commutative. X times y equals y times x. These are just individual real numbers, right? The components of a position vector. Okay, great. So that is a summary of what we did last time. This wonderful new object, the moment of inertia tensor, and this fascinating matrix relationship between angular momentum and angular velocity. So we're going to continue today with that. We're also going to have a discussion, a very general discussion of tensors. All right. And in doing this, we're going to have to introduce some slightly different notation. Behold, this new notation, this is the alternative notation, right? So we have been using subscripts x, y, and z for the components. We're simply going to relabel those to 1, 2, and 3. So the inertia tensor that we were looking at a moment ago, we had the Ixx, the Ixy, the Ixz. Now we use this simple transcription. We're going to call those 1, 2, and 3. Okay, so this is just the same thing with different decorations, so to speak. But it does open up doors for us. We can now start writing some wonderful formulas. That the matrix product, for example, okay, let's talk about that matrix product one more time. You remember when we wrote the matrix product, we wrote it like this, and we invoked the standard rules for matrix multiplication. So Lx, for example, this number here, the first component of the angular momentum, is gotten by forming this dot product of the first row here and this column here. Okay, let's look at how cool this is with the new notation. The new notation goes like this. Okay, so this is the same thing, right? In fact, this construction embodies the rules of matrix multiplication. You know, matrix multiplication is not commutative. You have to be very cognizant of which factors on the left and which factors on the right. And the general structure is this. When you form a matrix product, the index of summation, in this case, the index of summation is J. J is the second index here. Now, as it turns out, this inertia tensor is symmetric. So for the inertia tensor, it doesn't matter. But later today, we'll talk about some other matrices, which are like a rotation matrix. A rotation matrix is not a tensor. It's a rotation matrix. And in general, they are not symmetric. Okay, so here you have to be clear. This contraction, notice that J is the second index on the first factor, and it happens that this one here is a column vector. There's only one index there. But you could imagine multiplying two rectangular matrices, and then the familiar rules for matrix multiplication, written using this summation convention, is the index of summation is the last index on the first vector and the first index on the second vector. Okay, so this is again matrix multiplication. Right? In physics 89, we cover the matrix multiplication. All right, so let's talk about the inertia tensor once again, using this notation. The inertia tensor, when we first defined it, we were thinking of a collection of discrete particles, little point masses. Each mass was an ideal point. Okay, perfectly good thing to consider. We're also going to be interested in continuous mass distributions. And let's see how this new notation really shines, especially for the case of continuous mass distributions. All right, so here we go. Discrete, and this will be a nice opportunity for a side-by-side comparison. If you have discrete particles, okay? The left half of this comparison is going to be devoted to the case of the discrete point masses. Over here, continuous. Here we think of mass as a continuous, kind of like jelly. It's some sort of substance you can smear around. So continuous. And just want to point out, in electrodynamics, we have the same distinction. You can consider a collection of point charges. So these are ideal point charges. Each charge is an infinitesimally small point. Okay. You can also consider continuous charge distribution. All right, and there are different kinds of continuous charge distributions. You could have a parallel plate capacitor with a surface charge density smeared out over the surface. You could also have something like, think of a hydrogen atom and you think of the electron cloud as a three-dimensional volume charge density. So it's the same idea here. Let's revisit our results for the inertia tensor for the case of a collection of discrete particles. Here, unfortunately, the notation gets a little bit more cumbersome, even though we were hoping to enjoy simpler notation, and it will get better for the case of the continuous mass distribution. For the discrete mass distribution, it's a little bit annoying. Let's see what happens here. So the remember we had an equation for, let's position the paper like this. Okay, so we had this equation for Ixx. Okay, here's the central kind of difficulty. This x sub alpha, this is going to be a little bit more cumbersome to write. We're going to have to write this as the number one component of position vector alpha, right? Because in the new notation, we don't talk about x, y, and z. We talk about components 1, 2, and 3. So here we go. This thing that we used to call Ixx, we're going to call it I11. We have the sum over particles and the mass of the particle. That's identical to what we had before. Now, we must talk about the square of the length of this vector alpha. And here's where we have to introduce a new piece of notation. We're going to have to somehow indicate that this alpha is a particle label index, not one of the components 1, 2, 3. Remember, this is an integer. Alpha starts at 1, 2, 3, and if you have 1,000 particles, it goes up to 1,000. But we have to use parentheses to indicate that this index is on a different footing. It's not one of the 3 Cartesian components. Okay, so far so good. We got the R alpha squared like so. Now here's the really fun part. We have to grapple with this difficult notational issue. There's the R alpha. The 1 goes here like that. Okay. Yeah, some pretty funny notation, but we had to do it. Again, because we're using numbers 1, 2, and 3 to identify the 3 Cartesian axes. And so what we previously called x sub alpha, remember that's the x component of the position vector of particle alpha. Now we must write it like this. And you see we had to put parentheses. Somehow we have to convey the idea that alpha, although it's a number, and it could be 1, 2, or 3, etc., it is playing the role of a particle label. And so to put that on a different footing, we'll put parentheses there. Okay, so this formula now, again, the 1 conveys this x, right? We had x there, now it's a 1. Okay, so that's just a little unpleasant. Let's look at the same thing for a continuous mass distribution. So here, the organizational principle is a little bit different. We're going to simply integrate over all space. If there's no mass there, it's okay. That just means rho is 0. So we use rho as the familiar volume mass density. So we're integrating, and look how nice this becomes. We just have r squared minus r1 squared dv. And again, let's just remind ourselves, r1 equals x. Remember, the r vector is a special vector. As a vector, we write it as an r with an arrow over it. But when we talk about the 3 components, we call them x, y, and z. Okay, but you see this is a very nice formula. We don't suffer through all the madness of these indices here. And again, the key is the variable of integration. We're exploring all of space. Even if there's no matter there, we simply integrate over all space. This rho function, rho is a function of position, right? It's the density at your location in question. And that function, well, let's clarify here. Rho is a function of x, y, and z. The better way to write it would be rho is a function of r vector. Okay, it's a scalar field. All right, so having said that, let's look at an off-diagonal element. So that would be the I12. So we have the same remarks here. Okay, yeah, so that's just a little unpleasant here with these parentheses, but the important thing is we have to distinguish the particle label index alpha from the other number, which is the component. Okay, so that's, the parentheses again indicate that that alpha is not an index for a component, it's a label for the particle. So the alpha is a label. Okay. And then over here, the news just keeps getting better if you have a continuous mass distribution. So the I12, for example, we're going to integrate yeah, obviously a very nice simple formula. And again, the idea R1 is X and R2 is Y. They are simply identical. It's just different notation. And so this is saying you integrate over all space. You have the mass distribution at that location, and then you multiply by X and Y. So X times Y times the mass distribution, integrate over all space, and then flip the sign. And you're done. That's your component. Okay, so in this notation, we can write down a single formula, right? It was a little bit unpleasant that we had 2 different formulas. When we were talking about X, Y, and Z components, we had one formula for the diagonal elements. So this formula was useful for XX, YY, and ZZ. Very similar structure. Obviously for the YY, you're subtracting Y alpha squared. Okay. And again, this formula was valid for all of the off diagonals. So as long as these 2 indices are different, you use this formula. Now let's see how wonderful this new notation is. we can write down the entire tensor here like so. Okay. We are summing over the particles. There's the mass of the particle alpha. And now we have this nice construction. We have the Kronecker IJ symbol. Again, Physics 89, we'll talk about it in just a second. And then the R alpha I, R alpha J. Okay, that's nice. Let's compare that with the general formula over here. And we'll talk about this Kronecker Delta more in just a second. For the case of a continuous mass distribution, the IJ component of the inertia tensor is given by this nice integral. We integrate over all space. We have the volume mass density. Okay. And we got R squared. This is simply the square of the distance to the origin, right? Because the variable of integration is your position. Okay. So yeah, it's been a very interesting comparison here. We have the case of a discrete mass distribution. For example, on the homework assignment, we have a collection of point particles. And so this is the approach you could use for that problem. It's fully equivalent to the other formulas we were using when we had X, Y, and Z components. And for the case of the continuous mass distribution, it's very nice. It's understood that R sub I gives you X, Y, and Z. These are the coordinates, the Cartesian coordinates themselves. All right, so what we'll do here, we are going to talk about tensors in general. Okay, so we're going to have a general discussion of tensors. The course description, right, the official description in the catalog requires that we talk about tensors. However, this discussion is going to be a little too technical for the exam, so don't worry about tensors on our exams, right? So here we go with tensors. But as we go through this discussion, we'll see many interesting things. And we'll come to appreciate, for example, the dot product. We love talking about dot products all the time in physics. Think back to the earliest days of talking about the work energy theorem. You would figure out a dot product between a force vector and a differential displacement vector. So dot products are important. Dot products are also called scalar products. Let's write this out. Dot product equals, they're often called scalar. It's often called a scalar product because the resulting quantity is a scalar. It's a single number. It is not a vector. Scalar product. And there's another term, a third term, which is also very popular. It's called okay. So these three terms are identical. Okay. Let's take some time as we go through this discussion. We're going to see there's a whole wonderful world of tensors out there. This dot product, which is the same as a scalar product, which is the same as an inner product, we're going to see how we can compare this with a cross product. Okay. Notice a cross product is not a scalar. In fact, you could call it a vector product. And there's another kind of product, an outer product. Okay, notice the outer product is certainly not the same as the inner product. So, yep, all of these things await us in the wonderful world of tensor analysis. So again, we'll talk about tensor analysis just to appreciate some of the cool things that are out there, but don't worry about this stuff for the exams. It's a little too technical for the exams. All right, so let's begin with the definition of a tensor. Okay. And we're going to be interested in three-dimensional rotations. Okay. So that's important to point out. For what we're doing, we're interested in how things transform under rotations. So the question is, how do quantities transform under rotations? Okay, so something like a scalar product, of course, that's going to be invariant. If you have two vectors and you form the scalar product, for example, it could be 0, right? If the two vectors are perpendicular, scalar product is 0. And if you rotate both vectors to a different coordinate system, the scalar product is still 0. So that would be a rank 0 tensor. We're going to write this out in a moment. There are different tensors. So for us, the big question is, how do quantities transform under rotations? Okay. Vectors, they all transform a certain way under a rotation. And this may seem strange, but if you artificially construct a collection of 3 numbers, for example, the temperature, the pressure, and the humidity, or something like that, if you rotate to a different coordinate system, that does not transform like a vector. It's just a collection of 3 numbers, okay? So that may seem a little nonsensical, but the point is, a vector transforms a certain way when you go from one coordinate system to another under rotation. So we're interested in rotations. Of course, if you've had a special relativity or general relativity, you'll be interested in Lorentz transformations, okay? Transforming from one reference frame to another, there's a Lorentz transformation. And again, you have this notion of tensors, right? There are, obviously you're in a 4-dimensional space. And I mentioned that example because when you discuss tensors, there must be some group of transformations that you're talking about. For what we're doing, we're going to talk about 3-dimensional rotations, and we're going to insist that these objects have certain transformation properties under rotations. Okay, so let's begin by looking at vectors. Okay, so we'll have a general vector, just an arbitrary vector. And some time ago, we used capital Q for an arbitrary physical vector. I'm going to follow the book for this discussion. We will use lowercase q. Okay. And it's important to point out there are so-called active rotations and passive rotations. So we're going to look at a passive rotation, meaning here's this vector q, and suppose we have some coordinate system that we use to describe the vector q. Okay, so you would write this vector q as a linear combination of basis vectors. Okay, and this is what it means to write the vector as a linear combination of basis vectors. So these e hat I, these are basis vectors. We think of some unit vectors. The index I goes from 1 to 3. So we have an e hat 1, e hat 2, and e hat 3. So 3 basis vectors. And an arbitrary vector can be written as a linear combination. And these coefficients, notice q sub I is simply a number. It's the coefficient of this basis vector as you form this linear combination. Okay, a passive rotation means we're going to think of the same vector. There's no change to the vector. We're going to express it relative to a different basis. Okay, so it's the same q vector, but we're going to write it relative to a different basis. Okay, so before we do that, just a really quick remark. If you need to know these coefficients, you can recover the coefficients by forming a dot product. Notice if we form the dot product of both sides of this equation with one of the unit vectors, and again, we're assuming these unit vectors are orthonormal. That means they're mutually orthogonal. The dot product of any two different ones, that's 0. And they're normalized, so the dot product of a basis vector with itself is 1. So then you can easily get these coefficients, the qi coefficient okay. So before we go further, we do have to talk about a little technical item here, which is in this formula here, the index I is called a dummy index. Okay, it's really not there. You can see that by writing it out. This is Q1 times E hat 1 plus Q2 times E hat 2 plus Q3 times E hat 3. So there really is no I here. What we'd like to do is form the dot product of both sides with a basis vector. So if you take this formula as your starting point, then you should use some index other than I. Any index other than I would be a good idea for the dot product. So this is kind of a maximally bad choice to use the same index here, but it is justified once you form the dot product. So suppose we take this thing and on both sides we form a dot product with an E hat J. Like so, okay? Well, on the left-hand side, we have the Q vector dotted into the basis vector E hat J. On the right-hand side, there are 3 terms to think about. And as this index of summation I ranges from 1 to 3, there will be exactly one occurrence of the situation where you have a basis vector dotted into itself. And that's when the index of summation is equal to J, okay? So every other term in the sum gives you 0 because you have 2 orthogonal basis vectors. But when the index of summation is equal to J, then you have this dot product evaluating to 1. So the upshot is we've shown that Q sub J is equal to this dot product over here, Q vector dotted into E sub J. Once we've shown that, let's just write that out. The immediate conclusion is that E hat J dotted into Q is equal to the coefficient Q sub J. Okay, so the logical arrow goes like this. Starting from here, you form the dot product of both sides with E hat J, get this answer. Now this J is called a free index, okay? Free index. That's in contrast to this one here. This is called a dummy index. It's really not there. It's a placeholder, right? So it's called a dummy. Oops. Can't write dummy. Okay, that's a dummy index. You're free to rename it to something else, or some schemes of notation have no variable at all. They might use some funny symbols or something. The point is the I is really not there. You could write this out. It's just Q1 E1 plus Q2 E2, etc. So that's a dummy index. Well, for a free index, if this is true for any value of J, you're free to rename it. So then we go over here. So having renamed, so rename index. Okay, so in that sense, this is a valid equation. Those are some of the technicalities you have to worry about. But the point is you can extract these coefficients by getting the dot product. Okay, so to liven it up a bit, we'll bring in another choice, 3 different unit vectors. We're going to call them E prime I. Okay, so this is going to be a different basis. Okay. And so very much in the spirit of this result that we had here, the coefficients, again, it's the same Q vector, just a different basis. So the new coefficients will be a Q prime I. All right, dot product. Okay, So again, there's no change to the Q. That's why this is called a passive rotation. We're not changing the Q vector. For an active rotation, you have just one set of axes and you rotate that Q vector into a different position. That's considered an active rotation. For this discussion, we're considering the passive rotations. So it's the same Q vector. Okay, this could be, Q could be, say, the velocity of some particle. And different scientists prefer different coordinate systems. So they're going to disagree and argue vigorously about, the individual components. So the scientists in the original frame have these three components. And in the other frame, the primed frame, we have the Q1 prime, Q2 prime, and Q3 prime. Okay, so what we can do now is plug in our earlier result. This formula here, we plug it in here, and we get something remarkable. We are rewarded with a rotation matrix. Okay, so here's what we got. We'll put parentheses here to emphasize this is a prefactor, it's a coefficient. Very decorative, festive notation here, lots of decorations. Yes. Okay, so you see what happened. We took this formula, which is completely analogous to our original observation that you can get the expansion coefficient simply by forming a dot product with a basis vector. Then we plugged in the original expression. This Q vector can also be written as a linear combination here, this inside the circle, so to speak. Right, obviously it's an ellipse. Okay, so we plugged in this formula, and so we copied over the E hat prime I. That simply got copied over here. And we have this sum on J, and I changed the index of summation to J because that's a dummy index. And so the Q is that sum. Here's the unit vector J, and there's the coefficient Q sub J. Okay, wonderful. Now notice this has the structure of something with two indices, and you see we're summing on, we talked about matrix multiplication a moment ago. So this thing we're going to define to be R sub ij. Okay. And the indices I and j, they both range from 1 to 3. So this is a nice square matrix. It's a 3 by 3 matrix. It's called a rotation matrix. The other term you'll hear sometimes be, quote, direction cosines, right? Because these are unit vectors. If you form a dot product between two unit vectors, it's the cosine of the angle between them. So that's another term you'll hear quite a bit, the so-called direction cosines. So the rotation matrix consists of this array, right? You arrange these numbers into a 3 by 3 array. That's the rotation matrix. And so we can summarize here this nice result that the collection of coefficients obeys this transformation property. Okay, so that's the rotation matrix. Again, we're using our double-headed arrow, rotation matrix. Okay, it's a double-headed arrow because there are two indices. It's important to note that this is not a tensor, okay? The reason is a tensor is something like a velocity vector, et cetera, a force vector. It's something that exists in both frames. So you could have a velocity vector or a force vector. Different scientists with their own choice of axes have their own opinions about the coordinates. And then the rotation matrix tells you how to relate those differing opinions about the components. Okay, so the rotation matrix itself doesn't exist in one or the other frames. It's actually the relationship between the two frames. So again, it has a double-headed arrow because it's a matrix. It has two indices, there they are, I and j, but it does not transform like a tensor. Okay, so let's talk about this notion of transformation properties, and we'll make a nice summary here. It'll be useful to summarize some of the various things we've introduced. Okay, so this will be a fun table. So here we go. What we'll do is, it's useful to include the mass, the total mass. Total mass, we're going to see it's a rank 0 tensor. So let's begin like this. We have the name, the symbol. I'll probably go right, but that symbol. That can be a fairly narrow column. Again, we have to budget our space here, so let's be careful. The definition. And the transformation properties. Okay, and then let's put the let's put it like this: properties. I must squeeze it in, and then we'll put the rank. Okay, wonderful. We have a very nice table coming together here. And of course, this will be in my lecture notes, but just to make it an even better table, let's add a row here for the total mass. This is logical to include. Okay. We're going to see the total masses are rank 0 tensor. There are no free indices. Remember, the rank is the number of free indices. Okay, so the total mass, you know, we like to use capital M for the total mass. And the definition here, we're going to integrate over all space. We've got rho, that's the mass density, the volume mass density, dV. Okay. If you do this in a different frame, you're going to find the same total mass. Okay. So that we're going to see is a very interesting observation compared to other tensors. Let's get right to work with a rank 1 tensor. The center of mass . Right? You know, we compute a certain mass-weighted position. We've been using capital R. Now let's be careful here. Capital R with a single arrow, right? You know, we love to use capital R with a single-headed arrow. That's the center of mass. We must not confuse it with these rotation matrices, okay? For one thing, the center of mass has dimensions of meters. And these are pure numbers. Remember, they're direction cosines. If you can form the dot product between two unit vectors, that gives you a pure number. Okay, so the center of mass here, kind of a convenient way to write the definition is to multiply both sides by the total mass. So we'll go like this, MR, and this is when we're using vector notation. Let's be very careful here. We're going to integrate. There's the mass density. There's the position vector. Okay. So that's one formula. The transformation property, I'm going to write another formula in just a second. The transformation property, this looks a little bit confusing, but what's happening here, it's just because we use the same symbol, capital R. But the arrow makes it clear that this is the center of mass position in the prime frame, the new frame. It is equal to, just as we did here, right? This formula is the generic transformation law for a rank 1 tensor. So R prime is equal to this matrix. It's a rotation matrix times the old vector. And this is a rank 1 tensor. Okay, we're just about done. The one thing is, this notation has served us well with the arrows, but we really need to migrate to the new notation. Let's write the same exact formula in the new notation. We're going to write R sub I, and this is an integral. Okay, there's the mass density, and we do have the R sub I like so. okay, dV. So we're going to favor this new form. Of course, it is exactly the same equation as the one above, but now we're writing the various tensors with their indices. Okay. Now, of course, we want to talk about the inertia tensor. All right. There's also another tensor called the products of inertia tensor. We're going to really not emphasize that one so much. Let's go straight to the inertia tensor. Okay, the inertia tensor, as you know, the symbol here we got the capital I, the double-headed arrow, and we wrote down the formula a moment ago. Let's write it again just so we have a wonderful collection organized in a very nice fashion here with the increasing rank. This thing obviously is going to be a rank 2 tensor. Okay, the formula, you integrate over all space. You have rho, the mass density, the volume mass density. And now you have the R squared delta ij, the Kronecker delta. And you see I'm going to have to squeeze this in here. R sub I, R sub j, dV. All right, so obviously what happens here is this portion of the column gets bent like so. It can easily be done with a little extra ink. Yeah. The transformation law here is that the inertial tensor in the prime system, this can be accomplished with matrix multiplication. We're going to see that this is equal to the rotation matrix. Remember, there's the rotation matrix. We got the double-headed arrow. You have the inertia tensor in the old system. That's the I matrix with no further primes on it. And then we must have a transpose. Here's our symbol for the transpose. Okay. There it is. We did achieve our goal of fitting this into the table like so. Okay, and so you can see there's a wonderful hierarchy here. For a rank 0, this is one of the important messages. For a rank 0 tensor, there are 0 copies of rotation matrix. For a rank 1 tensor, you have 1 rotation matrix. Remember that R with the double-headed arrow, that's the rotation matrix. So there it is. Now for a rank 2 tensor, there are 2 copies of the rotation matrix. You have a rotation matrix for every free index. Notice this thing has 2 free indices, and so there are these 2 rotation matrices. Okay, the center of mass, that's a vector. It has 1 free index, and so when you transform it, there's 1 rotation matrix. Okay, so that's an overview. Now we have to revisit some of these topics we didn't go into a lot of detail here. First of all, let's quickly remark the Kronecker Delta. It is covered in Physics 89, but we should, for completeness, take a moment to remind ourselves, this thing here, the Kronecker Delta, what is that? Well, delta ij it's equal to 1 or 0. It's equal to 1 if I equals j. It's equal to 0 if I is not equal to j. Okay, so it's a pretty simple idea, really. The so-called Kronecker Delta. Okay, and obviously that's a lowercase Greek delta, Kronecker Delta. There it is. Just wanted to write that down. Okay, and it does transform. In a moment, we're going to talk some more about the rotation matrix and its properties. One of the properties is that the rotation matrix transpose, this twiddle is our symbol for transpose. And here's a fun one. This is the numeral 1 with the double-headed arrow. Okay, the numeral 1 with the double-headed arrow, that's the 3 by 3 identity matrix, right? 1, 0, 0, 0, 1, 0, 0, 0, 1, right? And you remember from Physics 89, that's the 3 by 3 identity matrix. And so that's this thing here. And so now we have kind of funny notation. We write the numeral 1 to convey this idea that it is a multiplicative unit. Remember, for multiplicative units, you multiply onto something and there's no change. And the same is true here. If you have this identity matrix and you multiply, suppose you multiply it by some square matrix, 3 by 3 squared, there's no change. This is the identity matrix. Now in our notation, we have to write it with the double-headed arrow to indicate we have a rank 2 object, rank 2 tensor. Okay. Now this, also the other notation was the transpose, right? This is the transpose. Okay, so now let's take a moment to bring together some of these concepts, and we will begin with the remarks we made earlier. Remember, we talked about the dot product, the scalar product, and the inner product. Different ways of saying the same thing. Okay, let's appreciate this, and let's appreciate the outer product. It turns out the outer product is useful to us as a means of producing a rank 2 tensor, and precisely it is one of the 2 ingredients in the inertia tensor, the outer product. Okay, so let's see how this comes about here. Okay, and we're going to be very careful with the notation. So the scalar product okay, if you have 2 vectors, let's say we have the lowercase a vector, and we're going to form a dot product with the lowercase b. So this is our notation. Fair enough. That's what we've been doing all along for these dot products. You know, what we want to appreciate is that if we agree that vectors are always thought of as column vectors, then something remarkable happens. You can write this as the following. Okay, and the crucial thing is that we're thinking of these vectors as column vectors. Well, if you transpose a column vector, you get a row vector. And now we must not write a dot. This is simply matrix multiplication. Okay, and we're going to draw some pictures to go along with that. So notice there is a dot here. And here, there's no dot. This is matrix multiplication. We do not write a dot. So there's no dot. Okay, this is matrix multiplication. And in fact, we have the usual rules for multiplying matrices. We have very clear rules for multiplying matrices. We know how to multiply rectangular matrices. So let's write this out in detail. Okay. Remember, the vectors are column vectors. Well, if you transpose a column vector, such as that thing right there, here's the transpose. A1 space A2 space A3. We're not putting commas there. That would clash with our other notation. That is a 1 by 3 matrix. Remember, when you talk about a rectangular matrix, the first number you say is the number of rows. The second number is the number of columns. This is a 1 by 3 matrix. Okay, and that we agreed is a column vector. That's a 3 by 1. Okay, so yeah, you see it works out perfectly. The usual rules for matrix multiplication now give us a 1 by 1 matrix. It's a 1 by 1 matrix, so we'll just drop the parentheses and just observe. Okay, so this is the scalar product, also called the inner product. Let's compare that with the outer product. Okay, so this is the inner product because we're summing over that index, right? So we can also write this in summation notation. This is the sum. I goes from 1 to 3, AI, BI. Okay, let's compare it with the outer product. And this one's kind of a mind bender, Let's look at the outer product. Okay. So suppose we reverse the order of these two factors. Okay. Remember what we said. This is a 1 by 3 matrix. Okay. A 1 by 3 matrix. This is a 3 by 1 matrix. Okay. And the usual rules for matrix multiplication, if you want to do a matrix product, the one thing you have to check is that the second number here equals the first number there. Then you can do that because you're going to be doing a collection of dot products. And these two numbers must match. Then you're golden, you can do this, and the result here is a 1 by 1 answer. Okay, the outer product, let's exchange the order of those two factors. B1, B2, B3. Okay, and again, that's a 3 by 1 matrix. That's our factor on the left. The factor on the right is a 1 by 3 matrix. That's our A1, A2, A3. Okay. Again, it's a perfectly well-formed matrix product. It's a 3 by 1 matrix times a 1 by 3. You can do that because the 1 equals the 1. That's the one thing you have to check when you do a matrix product. Having said that, we can write this out. And again, the usual rules for matrix multiplication tell us, first we choose a row in this matrix. Well, that row the first one just B1. And we'll multiply by the first column here. Well, that's just the A1. Okay, so we got the A1, B1. Okay, et cetera and so forth. A2, B1, A3, B1. Okay, now for the second row of the answer, you take this, the first row, the second row in this first factor, that's the B2, and you form the dot products, et cetera and so forth. So now we got the A1, B2, A2, B2, and A3, B2. And then finally with we got the B3 here, so A1, B3, A2, B3, A3, B3. Okay, we have a nice square matrix. It's a 3 by 3 matrix. Okay, wonderful answer. So we see that the scalar product, which is also called the inner product, the scalar product, which is also called the inner product, we have this sum, like so. The outer product, so written in tensor notation, this is just AI Bj. Okay. Here we've written this out as a 3 by 3 matrix. This is a rank 2 tensor, a 3 by 3 matrix. Let's just also remark, it is a rank 2 tensor. It's a rank 2 tensor because there are 2 free indices. You can count them, 1, 2. There are 2 free indices, so it's a rank 2 tensor. It's a 3 by 3 matrix because we live in a 3-dimensional space. So this is 3, and that's 3. Okay, rank 2 tensor. This thing is a rank 0 tensor. And if you like, you can say it's a 1 by 1 matrix. Okay, and let's observe that this structure does occur. We have seen this in the inertia tensor. Let's just look at our picture. Actually, it's right here. There it is. That's the outer product. You see the R sub I, R sub J. That's the outer product, and this one's the inner product. right? Because r squared, that's r dotted into itself. So there's the inner product of the r vector with itself, and there's the outer product. That's kind of nice that we have those two occurrences, right? R dot r and r outer product. So, you know, different books might have different funny notation. I won't even write the funny notation for outer products because we typically don't talk about them. But just one of our objectives today is to appreciate this. Okay, we have a question I just noticed in the chat window. Let me pull this over here. And would we be able to, then to say that any quantity is a tensor of some order? Okay, great question. It turns out that not every quantity is a tensor. So for example, a rotation matrix is not a tensor because the very framework is not there. We cannot say that we took a rotation matrix and we transformed it from one reference frame to another. In fact, the rotation matrix is more of a the tool that you use to transform from one frame to another. Another example I mentioned earlier is you can take three numbers such as the pressure, the temperature, and the humidity, right? So different scientists could measure these three numbers, but if you artificially arrange them into a three-component column vector, then it's not a tensor because if a different scientist is using a different Cartesian coordinate system, there's no rotation matrix that relates, right? There simply is no change to the temperature, there's no change to the pressure, and no change to the humidity. So yeah, for something to be a tensor, it has to transform according to this rule for a rank 1 tensor. For a rank 2 tensor, it's like this. And for higher tensors, let's get another piece of paper here. You could consider higher rank object. Let's go to rank 3 tensor. Okay, so this is a tensor, and typically when people talk about tensors, they use the capital T. We have to be a little careful. We like to use that for kinetic energy, but this is certainly not the kinetic energy if it has 3 indices on it. Yeah, this is a rank 3 tensor, but the point is it transforms according to the same rule. So this would transform with 3 copies. Okay. Okay, in the chat window, so a tensor, whatever transforms according to the rules. Yes, that's right. So the crucial thing is the transformation rules. And so in this hierarchy here, what we should point out is we were able to use standard matrix multiplication here. Notice what we did. This works out very nicely for rank 2 tensors. You can write the transformation rule with this rotation matrix, the inertia tensor, and then the transpose. So let's follow up on that for the rank 3. I think we should just follow up over here. This transformation rule, let's write this down using what we just said about matrix multiplication. This is a matrix product, and then there's another matrix product. Okay, so what we're going to do here, I'm having an inner debate. I think we're going to go for the micro font. Yeah, sometimes you got to go for the micro font. So this object here is the inertia tensor in the primed frame. So there it is, and I claim the camera has sufficient resolution. Okay, so we're going to work out the ij component. Okay, now that's pretty small. I admit that. Okay, that's almost too small. Maybe I'll copy it over later. But notice we have a rotation matrix. We'll go for an IK here. We have the inertia. Yeah, I'll copy this over. I just want to at least write it once here. We have the inertia tensor with a K, L. And then this is the transpose, right? So that's a rotation matrix. I would say with an LJ, but I have to swap them. So JL. Okay, yeah, I wrote it really small. Let's write it bigger. So this same thing, we're going to go over here and write it bigger. Okay, so what I said there, and I'm indicating now with these lines, is that the transformation rule looks like this. And since these individual components are numbers, we're welcome to change the order of these numbers. So now you see it, there's a nice structure that emerges. The primed inertia tensor, and we're talking about the ij component, is equal to the original one, the so-called unprimed, and here's the KL, okay? And then we have a couple of rotation matrices. Look at the structure. We have an R, I, K, and an R, J, L. And the crucial thing, this is the key to extending this to higher rank tensors, okay? You see what's happened, that the primed inertia tensor has indices I and J. Those indices occur as the first indices. It's the first index here, that's the I. It's the first index here, that's the J. And then you have the original tensor with indices KL, and those get mapped onto the second indices K there. So this prescription can easily be extended. Let's go for rank 3. You see, we can do the same exact thing here for rank 3. All we do is scoot up the paper. So we'll follow that prescription for a rank 3 tensor in the primed frame. Okay, we have an I, J, K. So what you do is you write the tensor in the unprimed frame. We're going to have to use an L, M, N, and then you write 3 rotation matrices. So you go R, 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 okay? And here we're using the Einstein summation convention. We're summing on the repeated indices. So sum on, right, the K and the L. Those are the repeated. This wonderful convention, if an index is repeated, you sum on it. If it's repeated in a product, okay? So here we have a rotation matrix, and what you do is you put the first index, we're gonna follow this prescription. You put the first index here, so this is Ri, J, K, and then these indices get summed like so, L, M, N. Okay, and it's understood we're gonna sum on the L, M, N. They go from 1 to 3. Okay, so again, this is a rather technical discussion. When you study Lorentz transformations, you'll have a very similar discussion. Rather than rotation matrices, you have these Lorentz transformation matrices. You can talk about boosts and rotation. Lorentz transformations actually include rotations, 3-dimensional rotations as a subgroup, but it's actually a larger group, a 6-dimensional group, because you have these boosts. Okay, so yeah, that's been a rather technical discussion. We just want to appreciate that we have different rank tensors, and this table is a nice collection to see the hierarchy, familiar things like the total mass, the center of mass position, and now the inertia tensor as examples of rank 0, rank 1, and rank 2. Okay, let's talk about some more concrete issues. In particular, I like to root out any sort of confusion. So let me issue a remark, something that could be confusing in the book. Okay, caution, we have a possible source of confusion. Okay, and this is an example 10.2, so possibly confusing wording. Okay, and here we are, example 10.2. Okay, the title is Inertia Tensor for a Solid Cube. Okay, it contains the following phrase, and here's the problem. We have this quote, rotating about a corner. Okay, and then the specification of axes, okay. Okay, so here's the thing. The inertia tensor, to compute the inertia tensor, you have to know the mass distribution, okay? But you also have to specify axes. So furthermore, this is confusing. There's no need for this object to be moving. The inertia tensor is just a property of a mass distribution. There's no need to have a state of motion. So what Taylor's doing here, he's saying that we're going to choose that corner as the origin, okay? So let's just remark, or I should say recall. Okay, in order to clarify this confusion, let's recall that the inertia tensor is a property of the mass distribution. So we'll say it like this: to compute I, to compute the inertia tensor, you need a mass distribution and a coordinate system. Okay, so and you have to choose an origin. So you certainly need some sort of mass distribution. In this example, you have a cube. It's a solid cube. That's a perfectly good mass distribution. But to compute the inertia tensor, you need to specify the origin. So that's a choice. Okay, so I just want to dispel the confusion here. You know, you can't just say, okay, we're taking a cube, it's rotating about one corner, and compute the inertia tensor. You have to say where you want the axes. For example, the axes could mimic the structure of the cube. They could run along the edges of the cube. And if you went to different axes, it would transform the inertia tensor. So that's just a quick remark to identify and dispel any sort of confusion here. Okay, so now we're going to move on to our next exciting topic, because we love working with matrices, right? In particular, eigenvalues and eigenvectors. That's got to be one of our favorite topics. Of course, when you go to quantum mechanics, you'll be doing a lot of eigenvalues and eigenvectors. Okay, so let's go to the so-called principle. Okay, and there are, here's where we have a really remarkable result. Say you go up into the Berkeley Hills and you find a boulder, some rigid object, but an apparently random shape. It's just a generic boulder. It turns out that there are three principal axes, and they're exactly orthogonal to each other. And the principal axes have the property that if they go through the center of mass, they have the property that if you spin the boulder about the principal axis, then the angular momentum is parallel to the angular velocity. In general, if you choose some funny axis of rotation, the angular momentum will not be parallel to the angular velocity. But the remarkable thing is that we have the existence of these three principal axes for any funny shaped object, even if it's a random object. You have three principal axes and they are mutually perpendicular. So for a principal axis, the angular momentum is a number. This lambda is just a number times omega. Okay, that of course is a very special state of affairs. We know the general situation. In general, the angular momentum is a matrix times the angular velocity. But what we're saying here is there are certain special directions. If you rotate this object about that special axis, then the angular momentum is parallel to the angular velocity vector. Okay, and again, that angular velocity vector defines the axis of rotation. Okay, so how can we calculate the principal axes? Well, we take those two formulas and we put them together. Okay, so principal axes will indicate like this. principal axes have this special property here. This second equation, we know that's true quite generally. Quite generally, the angular momentum is equal to an inertia tensor times the angular velocity. And this is the special state of affairs, very special. Okay, suppose we put these together. What can we say? Well, let's do this. We'll write it like this. We introduce some notation. Remember that numeral 1 with the double-headed arrow. Here's what we're seeing. The inertia tensor minus this lambda, this is going to be our eigenvalue, times the numeral 1. Remember, that's the 3x3 identity matrix. We did talk about the 3x3 identity matrix. Did we not talk about that a moment ago? Yep, there he is. You see the numeral 1 with the double-headed arrow. That's our 3x3 identity matrix. So we can say the following here. Okay, so this is what we conclude. Again, the philosophy here, the basic strategy for solving this problem, because we would like to find these special axes. Okay, so we use this observation that it's true quite generally that the angular momentum vector is equal to the inertia tensor times the angular velocity. That's true quite generally. Furthermore, under the special assumption that this is some eigenvalue times the angular velocity, some number times angular velocity, which obviously will point in the same direction as the angular velocity, we'll have a separate proof that these lambda is always positive. Okay, so positive or potentially 0. If you have like a collinear molecule, then you can have a null eigenvector if you're treating those as point masses. Okay, so we subtract, and it's necessary to put this numeral 1 here, right? So that we can have parentheses. For this to be a sensible subtraction, we have to subtract 3x3 matrix minus 3x3 matrix. Okay. Obviously, the numeral 1, if we were only looking at the numeral 1, this identity matrix, let's record that here. The identity matrix times omega is equal to omega. Okay. So this fact we put in here. Okay. So we inserted that into here, and then we have this structure. In both cases, it's a 3x3 matrix times omega. And since the difference is 0, we can factor out the common omega. Okay. Now you remember from Physics 89, if you have a matrix and if you can find a vector such that the matrix times the vector equals 0, then it must be true that the determinant of this matrix is 0, right? Because the existence of this vector means that you have a collection of coefficients, and you've formed a linear combination of the rows of this matrix that's 0. Okay, so here's the wonderful conclusion. The determinant of the inertia tensor minus lambda times our 3x3 identity matrix is 0. Okay, wonderful conclusion, because now we've reduced this to an algebra problem. Anytime we can reduce one of our problems to an algebra problem, that's great news, because we love to solve algebra problems. One little problem here, this is a cubic equation. You know, in general, cubic equations can be rather unpleasant. How can we convince ourselves that this is a cubic equation? Well, the quantity inside the parentheses here is the 3x3 matrix. And in particular, this lambda occurs on the main diagonal. So what we're doing is we're taking our original inertia tensor and we're subtracting a lambda for each of the 3 elements on the main diagonal. Okay, when you compute the determinant, those elements on the main diagonal get multiplied together. So yeah, this is a cubic. It's a cubic polynomial. In general, that can be rather unpleasant. Of course, on an exam, we would never ask you to solve a cubic equation. We can create problems where this immediately turns into a quadratic, which is considered a reasonable thing to do on an exam. Okay, so that's going to be our next order of business. We're going to talk about how you can find the principal axes. And for given like a homework problem, you may have some mass distribution. And one of the first things you need to do is figure out the principal axes. Okay. in some cases, you can use symmetry. So for example, if you have a cylinder, a right circular cylinder, and it's made of a uniform material, well, then you can argue based on symmetry that there must be a principal axis along the main axis of symmetry. And the reason is, if the angular momentum were not parallel to the angular velocity in that case, then you could rotate the system and the angular momentum should rotate with it. But that would be a contradiction because when you rotate that cylinder about the central axis of symmetry, the mass distribution is unchanged. Okay, so we've reached the 2 o'clock hour. I'm going to terminate the recording. Stop, right there, it says stop recording.